Okay, so good evening, everyone. Welcome to Focus Session 6, the immunity. I'm going to go ahead and finish up our discussion on hematology as we prepare for the exam, which is going to be on due Sunday or Monday, depending on which class you are in. So the agenda today, again, what's coming up? What should you expect from the class for the next week and a half? I want to cover the different types of immune cells, kind of what they do, what their purpose is. I'll cover clotting or hemostasis, and then I'll open it up to questions. Um, by this point of the lecture, ideally you've at least gone through objectives 1 and 2, specifically talking about the blood and red blood cells and kind of what they do. If you have questions about the red blood cells and how that stuff works, formation, please look at my video from last week. This week I'm going to basically wrap up some of the key highlights, primarily the immune cells and the process by which your blood will clot to prevent you from losing blood or too much blood when you have a puncture or a wound or a cut. Okay. So if you look at the schedule, you can kind of see that there's a couple discussions and practice exercises coming up for both classes. But again, our big ticket item is the Unit 3 exam for hematology coming up here on Sunday or Monday. And I'm going to introduce a little joke here. What is funny about humoral immunity? A very funny immune response, and that's why is that? Because you're associated with humoral immunity. And so this joke kind of relates to the different types of immune cells, specifically our adaptive immune system, where we have T cells and B cells. And depending on where your infection is, you're going to have a different immune cell that responds to that. So humoral immunity, when we think about humors, we think of our liquids in our body, but specifically this is blood. So whenever you have an infection that makes its way into your blood, you will have what's called a humoral immunity. Or sorry, a humoral, well, yeah, it is humoral immunity or a humoral reaction. Okay, so the main blood types or the main white blood cells we're going to talk about, there's typically 5 that we talk about in this class. We have our neutrophils, our monocytes, which become macrophages. We have our eosinophils, our lymphocytes, and our basophils. So the first way that the lecturer divides these is by labeling them as granulocytes or agranulocytes. So granules are small little dots, kind of little pimples that you can kind of see on the cells. The granulocytes are considered the neutrophils, the eosinophils, and the basophils. What these granules are they are a way for these cells to attack different types of foreign invaders. When I mention foreign invaders, I'm talking about bacteria, fungi, parasites, those kind of things. And then the agranulocytes, meaning without granules, are typically considered our lymphocytes and our monocytes. Um, so walking through our different infections. So depending, like I mentioned before, different types of cells will react in our immune system depending on the type of infection. So neutrophils, they'll typically be triggered by bacterial infections, but they are also triggered by some fungi, and foreign debris is kind of like um, non-human things entering your body. Our body can't detect whether something that goes in there is like, let's say, sand or something, but it will attack it like it's a microbe because our body doesn't know any better. Our immune cell is trained to recognize what's called self cells, so our cells, and everything else. So if it's anything in the body is not you, it'll attack it. Um, so neutrophils primarily will attack bacteria. Um, Eosinophils will typically target parasitic cells, and they're involved in allergic responses. And then basophils, they don't necessarily attack anything, but they are involved in allergic responses. Primarily, they release two chemicals in the body, histamine and heparin. So histamine, something that you've probably, if you have any allergies, um, you probably are very familiar with things like Claritin. Those are antihistamines. So what histamine does is it kind of will shut off your pathways. Um, and they do that to kind of, how do I say, to reduce the, let me go back. So histamine, what it'll do is it'll increase blood flow to a certain area that's infected. Um, because blood, like I said, these are white blood cells. This will make it easier for our white blood cells to get there. One of the drawbacks to histamine is that because of the increased blood flow, depending on where the infection is, you might have something where you start accidentally closing off like an air passageway. So things like pollens, bee stings, honey, you've heard of people getting that have severe allergic reactions to that. And they have to be given something that's like an EpiPen. The reason they have to get that is because the allergic response is so aggressive. The body is trying to attack this honey or this pollen that it increases the flow of blood to that area, which actually causes your blood vessels to expand. And it actually causes your tissues to, in our case, our airways to start closing because they have to expand so much. So basophils, again, they don't attack anything, but they release chemicals that help in our immune response. Histamine, which is primarily there to help increase the amount of white blood cells that go to the area. And then heparin, which is used for vasoconstriction. Let me go verify that real quick. I thought I had it over here somewhere, but I do not. And sorry, I'm a little bit disorganized. My dog is like barking in the background, so I'm trying to focus and I don't know what she's doing right now. So heparin is an sorry. So histamines are vasodilators, so they increase the blood flow, which I mentioned earlier. And then heparin is an anticoagulant. So certain microbes, what they will do is in order to prevent your white blood cells to getting to certain areas, they'll cause your blood they have clotting factors that will actually cause your blood to clot so that it slows down our immune response. The whole idea of a parasite or a foreign invader is to try to reproduce quickly in the host and try to take over or overwhelm the host defense. So imagine that we have a million white blood cells circulating our body and trying to protect us. When we get like a scratch or a cut or a bite, or we ingest something that has microbes like, let's see, rotten food, that microbe is trying to increase its size as quickly as it can to take over our body or to use our body for food. And so one of the ways that it can do that is by releasing coagulation to slow down our blood. So it gives these microbes time to reproduce. Um, heparin is an anticoagulant to keep it keeps the blood from clotting so that our white blood cells can get there in the appropriate amount of time. And then our two other cells, our lymphocytes or our monocytes, are what they call dormant macrophages. So macrophages are white blood cells. They are the big eaters. They basically go through and they eat or ingest any microbe that's in the area, usually pieces of microbes. Monocytes typically circulate in your blood, and then when you have an infection or an illness or a virus enters or whatever it might be, the monocyte then it transforms into a macrophage, it becomes activated, and then it'll start eating things that do not belong in your body. The neutrophils, monocytes, eosinophils, and basophils are part of our innate immune system. So you're going to hear terms called that we use in this class, innate immunity versus adaptive immunity. So innate immunity is our generic immune response. It doesn't matter whether I have a bacterial infection or the flu or COVID or pollen, whatever it might be, my body will attack those antigens or those foreign bodies the same. What lymphocytes will do is that lymphocytes are part of our adaptive immune system. So each microbe has certain pieces that identify that microbe as, let's say, an E. coli or a flu virus or um, a fungal infection. Our body can take those chunks, feed it back to our immune system, and basically it acts like a flag and it tells the immune system, hey, I just caught uh, this bacteria in the stomach. Here's a piece of the bacteria. I need you to make something that can attack this bacteria directly. The lymphocytes can then take that information and make very specific B cells or T cells that will target only that bacteria or that microbe. So lymphocytes can turn into two different things. It can make B cells, which attack invaders outside the cell, or it can make T cells, which attack infected cells. So T cells typically are involved when we have viruses. Viruses do not self-reproduce. They actually need to take over our cells to make more viruses. And so in order to do that, they enter our body. They enter the whatever specific cells they can attach to. They enter our cells. They overwhelm our cell, and then they take over, and then they use our cell to reproduce other viruses, and then those viruses spread. In order to destroy virally infected cells, we have to destroy our cells that have the viruses in them. So lymphocytes become T cells, and T cells have certain things they can do to basically pop our cells. It releases all the virus outside of the cell, and then our monocytes or our macrophages and our eosinophils, they can then go and start killing off all the virus parts. But it is harmful for our body to have too many virally infected cells because our body has to destroy our cells to get access to the viral cells. There are other things like viruses are very small in the microbe world, but things like bacteria and fungus, they're big. They're typically bigger than some of our cells. And so they cannot infect our cells, so they have to do their damage outside of our cells. And because they're more visible, our body can make what's called B cells, and these B cells release things that are called antibodies. You've probably heard of antibodies. When you get a vaccine, you sometimes create an antibody against that vaccine. What an antibody is basically a flag or a marker that is tailor-made for that bacteria or that parasite, whatever, that allergy, and it'll attach to those microbes, and it prevents the microbes from moving around and doing damage in the body. Then once the antibodies have this microbe surrounded, our monocytes or our macrophages, our eosinophils, our neutrophils can then come in and start destroying the microbe. Typically, things like parasites or bacteria, our neutrophils can actually, they kind of shoot little, kind of little microbial bullets, and they pop the membranes of bacteria, and then it makes them smaller, and then our body can go and eat them up. A lot of terms I'm kind of throwing out there, but biggest thing to take away is neutrophils, monocytes, eosinophils, basophils are part of the innate immune system. And then the lymphocytes are part of our adaptive immune system. And lymphocytes can turn into either B cells, which target, easiest way to remember this is non-virally infected cells, or it can make T cells that specifically will attack our cells that have a virus infection or cancer as well, which is sometimes considered a virus because it happens inside our cells. Kind of going back to what I meant by innate versus adaptive. So once we get into the next chapter in our digestive system, you'll notice that our digestive system is also involved in our immune response. But for the most part, the innate immune system, like I said, it doesn't differentiate between what's infecting you. It just goes attacks. So it's fairly quick acting. It's a non-targeted or broad response. So if I have an illness or let's say a cut in my arm, let's say my left arm, my immune system is going to put all its resources into attacking whatever could possibly be in my arm. Sometimes that causes damage to me. Think things like fever. Fever is very helpful for the body to fight off an infection, but having a fever for too long will actually start affecting our own cells. Um, there are some instances where the body might misinterpret your own cells as foreign, and so the body will start attacking itself. That's an autoimmune response. And then some instances where there are things that we take in or that we breathe that are not bad for us. Think honey, think smelling of flower or pollen. That stuff isn't actually going to harm us, but our body believes it will harm us. And it responds like this thing is deadly and needs to be stopped. And so sometimes the response from the immune system is worse than the infection itself. And that's what I mean by broad. It doesn't care. It's going to attack it the same way every time. Every time you have an illness, you're going to have a fever. You're going to have soreness. You're going to have like a lethargy, like weakness, and that's because the body decides to take any resource that you have that's extra and attack the infection first. And then if you survive it, then your body will start recovering. Um, and the biggest thing with this innate immune response is that there's no memory of the germs that infected you. So if I get the flu, let's say a very specific flu, flu strain A, my innate immune system will attack this flu virus, but it's never going to remember that I had the flu. So next year, my body's going to attack the flu just as aggressively and just as quickly as it did before. Um, The advantages of the adaptive immune system is that our body can learn to defend itself against any microbe that we've ever been infected with. There are things that you've been infected with already in your lifetime that you just never saw symptoms, but your body saw it, they attacked it, they destroyed it, and more importantly, the main thing about the adaptive immune system is that it created a memory. They create that you can create memory, be your memory T cells that specifically remember that infection. And so the next time your body sees it, the adaptive immune system already knows how to target it and it can eliminate it right away. This is kind of where things like vaccines come into play. A vaccine will give you, back in the day, they'd give you a dead version of the microbe. Nowadays, they give you like a piece of the microbe or the virus. Your body takes that, it says, this is foreign, I'm going to start attacking it. The adaptive immune system sees it, it remembers what it looks like, it starts making your memory cells. And then the next time you actually get sick from, let's say, COVID, the body already saw COVID before in the vaccine, so it knows how to target it the second time. Um, this is very helpful. Like I said, we can adapt to almost any infection. The biggest thing that we always have to worry about is time. So it is very slow to respond. So the question always becomes, can the body create enough of a defense before the microbe take overtakes our immune system, and then we no longer can survive or we can no longer function properly because the microbe did so much damage to our body that our immune system couldn't catch up. So it's always a give or take of, you can get sick. Most likely you will survive, but there are some instances where the microbes are so aggressive that we cannot wait for our body to catch up. We need help. We need to go to the doctor. We need to get external resources to help us fight that infection because our bodies just takes too long to figure out how to solve it. If anyone has any questions about that, that immune system is something that I am trying to specialize at the university level. So it's actually one of my favorite topics because I feel like our body is already made with everything that we need to survive. It's just how can we better optimize it so we're not waiting 2 weeks for our body to figure out that the flu is the flu, for example. The last topic I'm going to talk about is blood clot formation in our body. So this is part of objective 4, which is, let me just make sure that's the correct objective. Yep, objective 4, which is hemostasis. So hemostasis, the term hemostasis is just hemo, which is blood, stasis, which is stagnant. So it's keeping the amount of blood that you have. So in order to do that, your body goes through three different processes to stop your blood from leaving the body and then giving your body a chance to repair itself, so that you can maintain the amount of blood that you have. So three parts of the process are vascular spasm, then platelet plug formation, and then lastly coagulation or clotting. So the first part is a vascular spasm. So as soon as you get a cut or a puncture in your blood vessel, the blood vessel will quickly start constricting. So it's going to try to shut off blood flow as much as it can. Honestly, because you are a living organism, it can't just stop your blood flow outright. So it'll compress it as much as it can. You'll still have a little bit of blood going through because it can't just cut off blood all at once, but it slows down your blood flow to the area. This also does something that's very important where your your hemostasis or clotting is a positive feedback mechanism. So as soon as one platelet plug starts forming or one platelet starts clotting, um, the rest of your platelets want to start collecting together to clot also. In a normal day-to-day while you're walking, you don't want your platelets to just inadvertently start clotting themselves because that's going to cut off blood and you're going to have issues with that. So in your blood vessels or your blood, you have basically a kind of like an anti-coagulation thing going on to where it prevents the platelets from clumping together. However, the edges of your blood vessel have essentially another chemical that when the blood platelets sense that, it triggers the platelets to start clumping together and to start closing off the system. So again, the first part is just vascular spasm. It causes your blood vessel to constrict. It is temporary, but it does slow down the amount of blood that you're losing. The next part is the platelet plug formation. So platelet plug formation is triggered, like I said, by the broken blood vessels, and the collagen fibers on the edge of the broken vessel actually cause the platelet plugs to start forming up. Plug formation happens in three phases. You can kind of see on the right. You have adhesion, activation, and aggregation. So the first part, adhesion, that's where the platelets start collecting or binding with collagen, and they start releasing chemicals so that other platelets are drawn to the initial platelet to start making this web or this net. The platelets can also be activated to start changing their shape, and that allows the platelets to assume the shape that it needs to make sure that it covers your hole. So some cuts could be like a paper cut that's like long, it's very thin. That requires a certain shape of platelets. Others, if you get like let's say like a nail that goes through your hand or something, you're going to need a different type of patch for that. The platelets can change and form themselves however they need so that they can properly control the control the plug so that you don't lose blood. And then the last part is aggregation. And so the platelets can start combining with other platelets, and it'll also trap other red blood cells. And it'll start basically creating this big web, and eventually the platelet plug will form to where now you have a mixture of platelets, red blood cells, collagen fibers, and a bunch of other stuff to make your platelet plug, or your quote unquote clot. And then the last part is the coagulation. So coagulation is kind of like, I guess I kind of went a little too far. So coagulation is the combination of all the stuff, the platelets, the blood, the fibers, and it all creates one big clump of stuff that plug the red blood or the blood vessel so that you don't lose any more blood. These are typically temporary. So once the blood clot forms, and it's not necessarily covered, actually it is covered in this, is perfect. So once your blood clot has formed, your body will start repairing the outside of it. So if you've ever seen a YouTube video of what happens to your skin, basically your skin starts trying to repair itself, but depending on how big your hole is, sometimes you'll have this like dip. And that's because the cells don't have that support that they did before. And so your skin will kind of have this little dip whenever you have a big cut or a big bruise or a big opening. And so it'll give your body time to heal. And then once your body has healed, there is a process called fibrinolysis, where your blood clot will actually start dissolving. And then we'll start breaking apart the platelets, the blood cells, the fibrin, the collagen fibers. We'll start breaking it all apart, and then your blood vessel is repaired, and then you go back to living your normal day-to-day life. Um, that's a quick summary of it. I do like this image. This is one I used when I was studying because it kind of shows some of the chemicals involved with blood clot formation, because this is usually where I struggled, was the actual chemicals involved. The process of forming the vessel is pretty straightforward. In my opinion, you make this blood vessel smaller, you start getting all your platelets together in one little clump, and then you start clumping everything together with red blood cells and collagen fibers so that you can basically make some type of little plug for your hole so that nothing else gets out. And again, that's objective 4 if you want to go back and look at that in the notes. The stuff on the right is straight from the notes. So if you can remember that and connect it to the blood clot formation, you should be good to go. I did get a warning for 10 minutes remaining. So that's where I'm going to end it off. Does anyone have any questions while we're in here? And I'll check the chat, make sure no one's asking any questions. Okay, so if no one has any questions, thank you
Wait.
very much. Oh, hey, what's
Hey,
up?
I have a question.
Yeah, go for it. Um,
Me? Can you
oh,
hear me? I'm
yeah, I can
sorry.
hear you, Quinn. No, you're
Okay,
fine.
I'm trying to like drive and talk at the same time.
You're
So
fine.
my first question is about the thymus gland making the T cells.
Hmm.
Where are they made once the thymus isn't there anymore when it turns to adipose?
Oh, yeah. They're not made anymore. That's your question. So the thymus will create your initial immunity. It'll basically teach the body what is a self cell versus a non-self cell. But once the thymus is dissolved, we're no longer making new immune cells. The immune cells that are made, those are stored in our bone marrow. Um, and our body we naturally have some usually circulating. Our immune cells are able to repair themselves to a point, and you'll have basically cells. I'm trying to remember what the term is. It's hemolytic cells, I believe, or hematopoietic cells, I believe is the term. So those are basically blood cell stem cells. And so depending on what you need, whether it's blood, whether it's platelets, whether it's white blood cells, that hematopoietic cell will then turn into a white blood cell or a red blood cell or a platelet to then go and do what it needs to do. But
Okay, so
as
it's
far as the thymus, you're not like right now, I'm not actively making brand new immune cells. I already have all the immune cells I will ever need. technically stored in my bone marrow along with all the other red blood cells and platelets that I'll ever need.
Okay, and those can never be destroyed?
In your bone marrow and stuff,
Yeah.
yes, they can be destroyed. So your just like either if I suffer damage or when a white blood cell, I'll use the macrophages for example. When the macrophage starts eating up microbes or microbial parts, it'll eat until it dies. And then once it's dead, it basically becomes its own waste, and then other cells will then break apart the macrophage.
Okay, that
But
makes
yeah, so unfortunately, it's like, if for some reason we just went through some ridiculous infection and, in theory, yeah, you could technically run out of white blood cells. Um, in the realistic term, it's very unlikely that you'll have an infection that is so bad that it'll use up your white blood cells. You'll most likely die first before you use up your whole immune cells, if that makes sense.
got it. And then my other question is like when we're talking about immunity and infections, is it just what the cells that are being targeted per se? Let's talk about the T cells again and how
Mhm.
they attack infected cells. Are those blood cells that are being infected, or is it like all tissue?
So T cells will affect virally infected cells. So that could be typically when we talk about viruses, different viruses will infect different things. So think about like an influenza virus. Those like to target respiratory epithelial cells, so cells in our either in our lungs or in our respiratory channel. So those are, mucosal cells on that side. Um, Other viruses could attack things like in our liver, they could attack things in our stomach, they could attack things like in our bones. So these T cells will attack just virally infected cells in general.
Okay.
They're able to basically go in, they can use chemicals called perforins and granzymes. So perforins will make small holes in our cells, and then granzymes are enzymes that will dissolve our cell membrane to cause it to pop, and then all the virus stuff seeps out into our humors, and then our T cells or our macrophages can then come and start eating it all up.
Okay, got it. And then
Yep.
just my last question.
Mhm.
As far as blood clot, let's say if somebody gets just a normal blood clot from like poor circulation, does
Mhm.
what was it, fibrolysis, can that dissolve those blood clots too, or is it only like for wounds?
It's typically only for wounds. The fibrolysis, there's a chemical that gets released from our clots, particularly for our platelet plug, that
Okay,
let the body know that, hey, the 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 opening is sealed up, I'm no longer needed,
okay,
and that triggers fibrinolysis. Um, the regular, like the generic, like the blood clots that might just circulate in our body, those don't typically um, tell the body that they need to be dissolved, and so fibrinolysis process doesn't occur for those.
okay.
So
That makes
fibrinolysis is specifically for our platelet plugs because it uses certain chemicals to trigger the plug, and then it'll release other chemicals once it's ready to be dissolved.
okay. Got it. Thank you.
Yep, no problem. Good questions, Quinn.
Thanks.
Yep. Any other questions in the meeting? Okay, if not, feel free to reach out with any questions. And for those that are the hybrid, I will attach um, the keyword key question in the announcement. All right, thank you very much. Have a good rest of your day.